Welcome. In this video lesson we're going to master rates of reaction and equilibria, a crucial GCSE chemistry topic. We'll explore what reaction rate means, how we measure it, and the factors that make reactions go faster or slower. Using collision theory and activation energy we'll explain why these factors have their effects. We'll also look at practical experiments like reacting magnesium with acid and the disappearing cross experiment and learn to read rate graphs. In the second half, we'll tackle reversible reactions and dynamic equilibrium, understanding Le Chatelier's principle and how it's applied in real life, for example, in the Haber process to make ammonia. By the end, you should feel confident in these concepts, ready for that grade 9. The rate of reaction is essentially the speed of a chemical reaction, how fast reactants turn into products. Formally, it's defined as the change in concentration of a reactant or product per unit time. In simpler terms, it's how much of something, reactant or product, changes in a given time. For example, if a reaction produces 60 cubic centimeters of gas in 60 seconds, the average rate is 1 cubic centimeter per second. Reactions can be fast, like an explosion, or slow, like rusting. Knowing the rate helps us compare reactions and control them in practical applications. How can we measure how fast a reaction is happening? In experiments, we usually track a property that changes during the reaction over time. Common methods include observing mass changes, gas volumes, or color changes. Here are a few ways. Measuring gas production. If a reaction produces a gas, we can collect it to see how quickly it's formed. For instance, when magnesium reacts with acid, it produces hydrogen gas. We can capture the gas in a syringe and record the volume at regular intervals, or place the reaction on a balance and measure the mass dropping as gas escapes. A steeper increase in gas volume over time means a faster reaction. Measuring mass loss. Similarly, if a gas is given off, the mass of the reaction mixture will decrease. We can start with the reactants on a scale and see how fast the mass goes down. For example, reacting marble chips, calcium carbonate, with acid releases carbon dioxide. By recording the mass every few seconds, we see how quickly CO2 leaves. The faster the mass drops, the higher the rate. Observing color precipitate change. Some reactions change the solution's appearance. In the classic disappearing cross experiment, sodium thiosulfate reacting with acid turns a clear solution cloudy as sulfur forms. You mark a black X under the flask and time how long until it disappears from view due to the cloudiness. The sooner the cross vanishes, the faster the reaction. This method relies on a visible change, like a precipitate or color change, to gauge rate. Other methods. Any measurable change can indicate rate, like a change in pH if an acid or base is produced, or change in electrical conductivity if ions are produced. The key is recording something that varies with time. Often we plot a graph like volume versus time or mass versus time and determine the rate from the slope of the graph. Now that we know how to measure reaction rates, let's explore why different reactions have different speeds. This leads us to collision theory. Collision theory helps explain what controls the rate of a reaction. It states that chemical reactions occur only when particles collide with each other with enough energy and in the correct orientation to react. Not every collision leads to a reaction. The particles must hit hard enough to overcome an energy barrier. This minimum energy needed is called the activation energy. Think of it as a hurdle that reacting particles have to clear. If they don't have enough energy, they just bounce off each other unchanged. In summary, a reaction's rate depends on the frequency of collisions and the energy of collisions. The more frequent the collisions between reactant particles, the more chances for reaction, which means a higher rate. And if the particles collide with greater energy, enough to get over the activation energy barrier, a larger fraction of collisions will be successful and form products. You can imagine molecules as runners trying to vault a bar, the activation energy. Only those with enough speed can clear it. Next, we'll see how we can influence collisions and energy. According to collision theory, anything that increases how often particles collide, or how energetically they collide, will speed up the reaction. There are 5 key factors: temperature, concentration, pressure, surface area, and catalysts. Temperature. Heating a reaction makes particles move faster and collide more often and with more energy. This double effect makes temperature very influential. More particles have the required activation energy at higher temps, so many more collisions lead to reaction. For example, food cooks faster on high heat because the chemical reactions in cooking proceed quicker at higher temperature. Conversely, cooling things down slows reactions. That's why we refrigerate food to slow spoilage. Concentration of solutions. A higher concentration of reactants means more particles in the same volume. Particles are closer together, so they collide more frequently. Increasing concentration generally increases the reaction rate because collisions happen more often. For instance, a strong acid, high concentration, will fizz vigorously with magnesium, whereas a very dilute acid might react slowly. In gaseous reactions, increasing the pressure has the same effect as increasing concentration. Compressing a gas pushes particles closer together, leading to more collisions in a given time. Pressure for gases. If reactants are gases, raising the pressure squeezes particles into a smaller space. It's essentially the same idea as concentration for gases. More particles per volume means more frequent collisions. A reaction between gases will go faster at higher pressure. In a closed container, decreasing volume has this effect. Safety note. Because of this, gas mixtures at high pressure or concentration can be dangerous. For example, methane in a mine at high concentration can react explosively with air if ignited. Surface area of solids. If one reactant is a solid, breaking it into smaller pieces exposes more surface for collisions. Powdered or finely divided solids react faster than large chunks. This is because more reactant particles are available at the surface to collide with the other reactant. A dramatic real-life example. Fine dust like flour in a mill or wood dust in a sawmill can cause a sudden explosion if ignited, since the high surface area allows extremely rapid reactions with oxygen. In contrast, a single large piece of coal burns much more slowly than coal dust. Catalysts. A catalyst is a substance that speeds up a reaction without being used up itself. It provides an alternative reaction pathway with a lower activation energy. In other words, it lowers the hurdle so more colliding particles can successfully react. With a catalyst present, the reaction can proceed much faster, often dramatically so, even at the same temperature. Catalysts are not consumed by the reaction, so a small amount of catalyst can catalyze a lot of reactants. For example, enzymes in our bodies act as catalysts to allow biochemical reactions to proceed quickly at 37 degrees Celsius. In industry, iron is used as a catalyst to speed up the Haber process, making ammonia without getting used up. Importantly, catalysts only affect the rate. They do not change the final yield or position of equilibrium in a reversible reaction. They don't shift the equilibrium position, they just help it get there faster. So far, we've learned about the factors that affect how fast reactions go. Seeing these principles in the lab helps make sense of reaction rates. Here are two required practical examples. Magnesium plus acid, gas production. Magnesium metal, reacting with dilute hydrochloric acid is a reaction that produces a gas. Magnesium plus 2-hydrochloric acid yields magnesium chloride and hydrogen gas. You can observe the rate by collecting the hydrogen gas. Typically, a strip of magnesium ribbon is dropped into a flask of hydrochloric acid and quickly sealed with a rubber bung connected to a gas syringe. The syringe plunger moves out as hydrogen bubbles off, and we record the volume at regular time intervals, say every 10 seconds. Alternatively, we could cover the flask mouth with a piece of cotton wool to let gas escape but prevent liquid splashing out and measure the mass loss as hydrogen escapes. The reaction starts fast, lots of acid particles to collide with the magnesium surface, and then slows down as the acid is used up. If we plot volume of hydrogen versus time, we'd get a curve that rises quickly, then levels off when the magnesium is all gone. We can repeat the experiment with different acid concentrations or temperatures to see how the rate changes. For example, using a higher concentration of acid produces the same total volume of hydrogen but in a shorter time, a steeper, faster curve, compared to a dilute acid. Sodium thiosulfate plus hydrochloric acid, disappearing cross. This reaction produces a solid sulfur precipitate, turning a clear solution cloudy. Sodium thiosulfate plus 2-hydrochloric acid yields 2-sodium chloride, sulfur dioxide gas, sulfur solid, and water. In practice, you place a conical flask on top of a piece of paper with a black X marked on it. The flask is filled with a clear solution of sodium thiosulfate. Then you add hydrochloric acid, swirl, and start a timer. The solution slowly turns yellow and opaque as sulfur forms. You watch from above and stop the timer when the X is no longer visible. The time it takes for the cross to disappear is a measure of the reaction rate. Shorter time means faster rate. This experiment is great for investigating the effect of temperature or concentration on reaction rate. For instance, you can do the reaction at different temperatures by warming the solutions in a water bath. Higher temperature makes the cross disappear sooner, showing an increased rate. Or you can vary the concentration of the thiosulfate solution. Lower concentration, more diluted, makes the cross stay visible longer, indicating a slower reaction. One detail to note is that this method is a bit subjective. People might disagree on the exact moment the X disappears, so averaging repeated trials is wise. For more precision, a light sensor can be used to detect the change in turbidity instead of the human eye. These experiments reinforce our understanding. More concentrated acid makes magnesium react faster, more frequent collisions, and higher temperature makes thiosulfate react faster, collisions more energetic, exactly as collision theory predicts. We often use graphs to analyze reaction rates. Consider a graph of product formed or reactant remaining versus time. The slope or gradient of the graph at any point represents the reaction rate at that moment. A steep slope means a fast rate, while a flatter slope means a slower rate. At the very start of a reaction, the graph is usually steepest. That's because concentrations are highest initially, so collisions are very frequent. The reaction is at its fastest. As time goes on, reactants get used up and their concentrations drop. Fewer particles are available to collide, so the reaction slows down and the graph slope becomes less steep. Eventually, one of the reactants will run out or the reaction reaches completion. At that point, no more product is formed and the graph levels off, slope becomes zero. If we compare two different scenarios on the same graph, say the same reaction under two different conditions, a faster reaction will have a steeper curve and finish earlier, level off sooner. For example, if we perform the magnesium plus acid reaction with a more concentrated acid versus a dilute acid, both might ultimately produce, say, 50 cubic centimeters of hydrogen, assuming the same amount of magnesium is used, but the concentrated acid will get there much quicker. Its graph climbs sharply and levels off in a short time, whereas the dilute acid's graph rises more slowly and takes longer to flatten out. The initial rate is often compared by drawing a tangent to the curve at time zero. The gradient of that tangent line gives the initial rate. Being able to interpret these graphs is important. Let's quickly recap the key points on reaction rates. The rate of reaction refers to how fast reactants are converted to products, quantified as change in amount or concentration per time. Measuring the rate involves tracking changes like gas volume, mass, or appearance over time, for example, cubic centimeters of gas per second, grams per minute of mass loss, or seconds for a color to change. Collision theory states that particles must collide with enough energy, known as activation energy, for a reaction to occur. More frequent collisions or higher energy collisions lead to a higher rate. Factors that increase the rate include higher temperature, higher concentration or pressure, greater surface area, and catalysts. Rate graphs show that the slope represents the rate. Reaction graphs start steep, indicating a fast rate initially, and then flatten out as reactants are used up. A steeper graph means a faster reaction under those conditions. Now that we've covered reaction rates, let's switch gears and look at the other side of this topic: reversible reactions and equilibrium. Not all reactions go to completion in one direction. Some are reversible, meaning the products can react to reform the reactants. We denote this with a special double arrow. A simple example is heating blue hydrated copper sulfate. It turns white as water is driven off, but if you add water back, it turns blue again. The reaction can go in either direction. In a closed system, where none of the reactants or products can escape, reversible reactions can reach dynamic equilibrium. Dynamic equilibrium means the forward and backward reactions are still happening continuously, but at equal rates, so there is no overall change in the amounts of reactants and products. In other words, the system has achieved a balance. As fast as reactants turn into products, products are turning back into reactants. The concentrations of all substances remain constant, though not necessarily equal. It's called dynamic because molecules are still reacting, and equilibrium because, macroscopically, everything appears unchanging. To visualize this, imagine walking the wrong way on an escalator. If you walk upward at the same speed as the escalator moves downward, you stay in the same place. You are moving, but you make no net progress, just like dynamic equilibrium, where reactants form products and products form reactants at the same rate, so there's no net change. Now, what happens if we disturb a system at equilibrium? Le Chatelier's principle gives the answer: if a change is made to a system at equilibrium, the position of equilibrium moves to counteract that change. In essence, the system responds by opposing your change. It's like the reaction pushes back against the disturbance to try to restore balance. This applies to changes in concentration, pressure, or temperature. Let's break it down by the type of change. Concentration changes. If you add more reactant, increasing its concentration, the equilibrium will shift towards the products to use up the added reactant. It's as if the reaction tries to consume the extra reactant by making more product. Conversely, if you remove a reactant or add extra product, the equilibrium shifts towards the reactants, the backward direction, to replace the missing reactant or to consume the extra product. In short, increasing the concentration of a substance drives the equilibrium to use up that substance. Decreasing its concentration drives the equilibrium to produce more of it. Pressure changes. For gases, if you increase the pressure on a system at equilibrium by decreasing the volume of the container, the equilibrium will shift in the direction that produces fewer gas molecules. Fewer gas molecules exert less pressure, so this shift partially relieves the pressure increase. If pressure is decreased, the equilibrium shifts toward the side with more gas molecules to build the pressure back up. For example, if one side of the reaction has 2 moles of gas and the other side has 4 moles, a high pressure will favor the 2-mole side. Temperature changes. If you increase the temperature of an equilibrium mixture, the equilibrium will shift in the endothermic direction, the direction that absorbs heat. It does so to use up the extra heat you added. If you decrease the temperature, cool the system, the equilibrium shifts in the exothermic direction, the direction that releases heat, to produce more heat and counteract the cooling. Every reversible reaction has an exothermic direction and an endothermic direction, the opposite. Le Chatelier's principle lets us predict which way it will shift. Add heat, favor endothermic. Remove heat, favor exothermic. Catalysts. Adding a catalyst does not change the position of equilibrium. A catalyst speeds up both the forward and reverse reactions equally, so it helps the system reach equilibrium faster, but it doesn't affect the equilibrium concentrations. Think of it like oiling a door hinge. The door can open or close more easily faster, but it doesn't change where the door eventually rests. One famous application of equilibrium principles is the Haber process for making ammonia, NH3. This is the reaction of nitrogen and hydrogen gas. N2 plus 3H2 yields 2NH3, with a delta H of minus 92 kilojoules per mole. Nitrogen is very unreactive, but with the right conditions it combines with hydrogen to form ammonia. The forward reaction, making ammonia, is exothermic. It releases heat, and it produces 2 moles of gas from 4 moles, 1 N2 plus 3 H2. The challenge industrially is to get as much ammonia as possible, as fast as possible, in an economical way. Let's see how Le Chatelier's principle guides the choices of conditions. Pressure. There are 4 moles of gas on the left side of the equation, versus 2 moles on the right. Increasing pressure pushes the equilibrium toward the side with fewer gas molecules, that is, toward ammonia. In the Haber process, a high pressure, around 200 atmospheres, is used to favor ammonia production. Higher pressure also increases the rate of reaction because the gas molecules are closer together. However, extremely high pressures are costly and dangerous, so around 200 atmospheres is a practical compromise. Temperature? The forward reaction is exothermic, so lower temperatures would favor the forward direction, more ammonia. But if it's too cold, the reaction rate would be too slow to be practical. The Haber process uses about 450 degrees Celsius, which is a compromise temperature. It's low enough to get a decent equilibrium yield of ammonia, around 15% per pass, but high enough to have a reasonable rate of reaction. This compromise is key. A moderate temperature gives up some yield, but vastly increases the speed of production. It makes no sense to use a temperature so low that you'd wait ages for slightly more yield. Catalyst. The process employs an iron catalyst with potassium hydroxide promoters to speed up the attainment of equilibrium. The catalyst does not change the equilibrium position, but it increases the rate at which equilibrium is reached. Without a catalyst, even at 450 degrees Celsius, the reaction would be too slow to be economical. With the catalyst, nitrogen and hydrogen rapidly form ammonia, and the equilibrium is achieved faster. This allows the process to run continuously with good throughput. Continuous removal of ammonia. In the industrial process, ammonia is continuously removed from the reaction mixture by cooling and liquefying it out. This has the effect of shifting the equilibrium forward. As per Le Chatelier's principle, removing a product drives the reaction to produce more product. Meanwhile, any unreacted N2 and H2 are recycled. This way, although each pass through the reactor yields only about 15% ammonia at equilibrium, the ongoing removal and recycling approach nearly 100% conversion over time. Thanks to these optimized conditions, high pressure, moderate temperature, catalyst, continuous removal, the Haber process can produce ammonia on a large scale. This ammonia is crucial for making fertilizers such as ammonium nitrate, urea, and so on. The development of the Haber process in the early 20th century revolutionized agriculture by providing a steady supply of nitrogen fertilizer, greatly increasing food production worldwide. It also had applications in explosives, but its impact on food supply is arguably most important. This is a prime example of chemical equilibrium principles in action. A real-life scenario where understanding the rate versus yield trade-off and Le Chatelier's principle was the key to an industrial breakthrough. Let's summarize the key takeaways from rates of reaction and equilibria rate of reaction. The speed of a reaction, often expressed as change in concentration of reactant or product per unit time. Fast reactions, high rate, produce products quickly. Slow reactions, low rate, take more time. Measuring rate. We measure reaction rates by monitoring changes in quantities over time, for example, volume of gas produced, mass lost, or appearance, color, or clarity change. Collision theory. Reactions only occur when particles collide with sufficient energy, the activation energy, and proper orientation. A higher frequency of collisions or collisions with more energy leads to a higher rate. Factors affecting rate. Temperature, concentration, pressure, surface area, and catalysts are the main factors. Increasing temperature, concentration, pressure, or surface area increases the rate by causing more frequent or energetic collisions. Catalysts increase the rate by providing an alternative pathway with lower activation energy. They are not used up in the reaction. Dynamic equilibrium. In a closed system, reversible reactions can reach a state where forward and reverse reactions occur at equal rates, so concentrations stay constant. This is dynamic equilibrium. The reaction hasn't stopped, but for every molecule that reacts, another is produced in the reverse direction. Le Chatelier's principle. If you change conditions of an equilibrium, concentration, pressure, temperature, the system shifts to oppose that change. For example, adding reactant makes more product, shifts right, increasing pressure favors the side with fewer gas molecules, raising temperature favors the endothermic direction. Catalysts don't change equilibrium positions, they just help reach equilibrium faster. Congratulations! We've covered a lot, from what reaction rate means and how to measure it, to why and how various factors change the rate, and finally what happens in reversible reactions at equilibrium, and how changing conditions affects them. Remember these key ideas, and you'll be well prepared to tackle any exam questions on rates and equilibria. With a solid grasp of collision theory and Le Chatelier's principle, you have the tools to explain a wide range of chemical behavior, a hallmark of a grade 9 chemistry student. Good luck with your studies.